Today we have Mike Farb, who will be presenting his work on SafeSlinger, recently released. Mike Farb joined Carnegie Mellon CyLab as a research programmer in 2010. He received his BA from Beloit College. Hope I said that right.
Yep.
In 1995, and as a mobile device software developer, has worked in publishing, transportation, and security. While at Nouveau Media, a pioneering digital publisher of the late 90s, Michael created software to manufacture their Rocket ebook reading devices. At FedEx Ground, Michael built mobile software for 3 generations of pickup and delivery scanners and created mobile applications to replace mainframe processes that manage delivery quality. He now is working with researchers at CyLab to provide smartphone end users with practical solutions for securely exchanging their identity data. Please welcome Michael Farb.
Thank you. Let's get started here. So yes, I privileged to work on this project called SafeSlinger with several researchers here at CyLab, and it's definitely. And if you remember the old joke on the old series Star Trek, the doctor would always complain to the engineer or the captain, I'm a doctor, I'm not an engineer. I'm a doctor, I'm not a moon shuttle conductor. Well, in my case, it's a little reverse. I'm an engineer, not a doctor, but I get to work with doctors as part of my work. Adrian Perrig and John McCune have been mentoring me in this project, and it's been great fun to work with them. But if that's a little bit of fun about me, here's something that's not so fun. This is a photocopy of a credit card application that was filled out on my behalf in 2000 or so. And as you can see, this has all been faked. They filled out just a bunch of bogus information. I've blacked out my address for privacy. This is my actual Social Security number under here, by the way. So this is a little bit of an example of when we're trying to authenticate our data amongst other people. This is an analog sort of man-in-the-middle attack, if you will. They were able to monitor my mail in such a way before it got to me that they were able to learn my Social Security number, as well as take this information, fill out the credit card application, and then there wasn't much verification done by the particular bank to verify that I was a real person and that I approved of this credit card. So they were able to charge some money to this accountant. I have a nice thick file that was my part of trying to undo that over the course of time. And if that is an analog attack, then we can also look at some digital attacks. You don't have to go too far to find out some of the news articles and things that are going on out there. We are using our cell phones to exchange information more and more. And though it appears that since we're the only people that are using them, that are typing information, no one can see us do them, put that information into our computers, send it to some other computer that, these things are being captured wirelessly. Our wireless channels may not be safe for our cellular providers. Even if we send an email to the person that we intended to send it to, we may mistype them. In this case, the GoDaddy group was able to squat and register fake domain names for common misspellings of a lot of large companies. And they got a whole lot of information that they shouldn't have been party to. So that's not so good. So we're going to talk a little bit about trying to exchange easily ad hoc public keys between groups of people, 2 or more, and how we do that. We're going to talk a little bit about a prior project, SPATE, which ended just as I joined CyLab a couple of years ago, and the current work that we're calling SafeSlinger, and the engineering choices that we've made along the way for usability, performance, cross-platform issues, and talk about what we want to do in the future with this. So, give you a little bit of setting. People want to meet and securely communicate later. Could be people at a conference, researchers, business people having lunch, students at a party. But as we meet, we don't necessarily have a commonly trusted infrastructure. We may not all belong to part of a large-scale corporate or institution-wide key infrastructure or certificate authority. So we want to be able to create a cryptographic key and exchange it in a secure fashion. The problem is that we exchange authentic information between group members, and that's what we're trying to do. That's our goal. We need to collect exactly one piece of information from each group member. It doesn't need to be a bit, but some block of data. That's our identity data. A key, a phone number, or some combination. We only want to disclose the information to other group members, and we want to enable this for remote operation. It may not be convenient for people to necessarily meet together. With those authentic public keys, and we made sure that the keys we've exchanged digitally belong to the people that we expect them to belong to, the members can encrypt messages to hide information. We can attribute messages to other group members and establish a shared key with any subgroup in a secure fashion. So some prior solutions to this, the PGP key signing party was one way for people to meet physically and assure each other of their actual presence. We're all in the room. We can compute the keys that we can run math on the keys that we're sharing together to make sure that they're going to be the ones we eventually share digitally later. But it requires some sophisticated knowledge to do this. And the public key infrastructure, we might publish our information, our keys on a key server, but then we're trying to validate that people are who they say they were digitally. And so we don't have a combination of the two yet, digital and physical. So the challenges that we want to overcome, we want to provide secure operation with careless users and a powerful local adversary who can monitor our messages and potentially alter our messages. We want most users to avoid clicking OK. I get a dialog box on my cell phone and it says to do something. I just want to get past it. I just want to finish what I'm doing. Group members may be malicious, attempting to impersonate other members. We want to be able to detect that. Counting can be hard for large groups of more than 8. The accuracy of who, like if I tried to count the number of people here, I might take a while to do it. If I were trying to do it quickly, my accuracy would quickly degrade. We want to enable remote operation. We want to be able to do this over the phone, validate each other over the phone. We can assure each other of our presence because we recognize each other's voices in real time. Do you want me to do something about that? There's no information leaked to outsiders, even if the protocol fails. So this is something that we have to have. Now, the project that much of the SafeSlinger work is based on was SPATE, and I'm going to run through a little bit of the details on that. But one of their observations as a result of that project was that most groups are small, that people want to meet and exchange secure information, and we want to speed up key exchange for groups of more than 8. So with SPATE stands for Small Group PKI Less Authenticated Trust Establishment. And it's designed to be efficient. A member should be able to do a series of very easy actions, just 3. Select the data I want to share, count the number of people in the group, and compare some value on each phone so that we can assure each other that the information that we exchanged is accurate. And we want to have just a simple comparison in such a way that if only one user pays attention, it protects the entire group. So SPATE had about 4 main steps here. Selection and counting. The first step, which was the users need to involve themselves in, we just select our data, we count the number of people, and we begin the protocol and start sending messages between phones. The user indicates what data is to be shared and the size of the group. Second step, collection. The phone broadcasts and collects data. 3, verification. The user will verify the group members share the same data. We're going to display the same data on every phone, and everyone will check to make sure that's the same. We want to check the consensus of every user. Once the users transmit that everything is correct, we want to validate that among the group and then save our data. So the mechanism to communicate between phones and SPATE used Bluetooth. I won't go into too much technical detail here, but they used, at most 8 phones can support a Bluetooth piconet. You would photograph a barcode on the phone to expedite the discovery process. If everyone has tried to do discovery and pairing between Bluetooth devices, you can kind of pull and see this long list of other things that are in my personal area network. But to avoid doing that, we display a barcode of the address, the Bluetooth address on the phone, and then take a picture of it, and that is a quick way to transfer to the other phone. Ad-hoc 802.11b is another possibility, and I think on the phones they use the Nokia E51 in this project. They had to reinstall the operating system to gain that functionality, but that's not really something you want most users to do. That's a pretty technical process. And potentially we might consider using some kind of server, some kind of online bulletin board to exchange messages. And at the end, each device will acquire a potential list of data, and we want to make sure that each bit of data was sent by the person that it came from. At the end, verification. Actually, right before the end, this is step 3. User-friendly comparison, thank you. User-friendly comparison to reduce errors, a simple hash on the screen, a small visual checksum, which takes the form of an image. We'll show a picture of that. And as I said before, detection by one user protects the group. We want to construct a one-time signature for each member of the group to send around to attest whether or not the information matched on the screen or whether or not there was some difference in any of the hashes. So we'll start off with our data, and we'll construct a nonce, a number used once. We'll combine those 2 values together. We'll concatenate them, and we'll hash them. We'll come up with our commitment A, and we'll actually now send to other group members. If I have A, B, and C in this group, 3 people, I'll send my commitment out first. And then I'll receive the commitments from the other users. Once I've done that, and I know who my users are, I can then broadcast my data and my nonce to them, and they can validate, they can compute the same hash and make sure that it comes up with the same commitment, and they can send their data and their nonce to me, and I can perform the same validation. Of course, if it doesn't match, then I want to do something about that. The verification takes the form in SPATE of a T-flag, which is this image constructed out of simple colors and blocks to display 24 bits of information. And it's oriented with these 2 black bars in a T so that you know which direction you should be comparing with other phones. But it's a fairly simple way of describing or comparing between phones. So we just need to count the number of people present and compare these checksums. But at the end there, we haven't really shared the answer, whether or not everything matches. Users suffer from this issue, so I want to get out of this protocol. I want to end it. How do I get past it as quickly as possible? So I just want to click OK to continue. So if the slow user, the last person to give an answer of whether or not everything matched, had a problem, then what do you do? So we create a one-time signature. We construct a multi-commitment hash tree, and we share different values of that tree. I'll show you to determine whether or not there's a match or not a match. If everyone sends out a match one-time signature, then great. Then we know that the data that was shared earlier by all people is valid, and we keep it. If we have any errors or no signature from someone, then we know that we just need to discard all the data. So similarly to the other diagram, we start off with, instead of one nonce, now two. One is for the match answer, and one is for an error, or no match. And we have our data. So then we hash each of those nonces. We concatenate them and hash them again, and we come up with this nonce D. Now we take, similarly before, that nonce with our data, concatenate them, and come up with our commitment. The commitment serves as a verification value, as we've seen before. Then the diligent users are going to report errors. That's the idea. We send out our commitment to other group members. Next, now we've collected our commitment from other group members. We also take our data and our nonce, we send that out. We receive it from other group members. We construct a duplicate hash to make sure the values are equal. If I want to tell the group that I see some, actually before I describe that, at this point, once we have the data and the nonce from everyone in the group, we can order all those pieces of information in some predetermined way, hash it, and come up with that visual hash. And that's what you see there. 24 bits of that hash are that T flag. But if I see some difference in any of my group members, I want to say there's no match, and I want to send these two values, n prime m, and nonce e. Because other users will be able to then create a hash from nonce e called nme, combine it with n prime m, and if they come up with the nonce, then we know that the person indicated there is an error. But of course, we don't want to do that. We found a match, so we deliver the opposite hash. And so this last step is where we share these one-time signatures. Now, once we've collected match from everyone, all end phones claim success, then it's valid and we can save that data. A little bit of performance. The time spent in this protocol is mostly taken up by the process of one leader acting as a host among some of the members in the group. So they take their phone and they photograph the barcodes on all the other phones, because that's how the Bluetooth PicoNet works. One acts as a host, the others act as clients, and communication is distributed in that star fashion. So if we could eliminate that portion of it, maybe we get a little more speed. Some drawbacks to SPATE in regards to our goals are that the barcode imaging doesn't work really well outdoors in bright sunlight. We get a lot of glare. The images don't photograph well. iPhones have an implementation restriction for Bluetooth. They don't implement the full Bluetooth protocol. So it's not a great choice for cross-platform implementation if I want to implement this on Android and iPhone and Symbian or Nokia. Users can simply click OK. Actually, at the hash comparison, even though we've now shared the answer, what makes people actually look? I could just click OK. Yeah, it matches. Fine. I'll just keep going. Leader selection is a little cumbersome, a little error-prone. The outsiders can learn all our information. Even though we've achieved authentication now, people who can monitor our wireless Bluetooth traffic now have learned the information we've shared. And this can't be performed remotely over the telephone. This is an in-person protocol. So with SafeSlinger, the main innovations are that the phones can communicate via an internet server, in our case, an online bulletin board, which is a nice cross-platform solution to be able to share data. But now I need to protect that data, because now I've opened it up to the internet, right? So we want to protect it in such a way that only group members can learn other information. If it succeeds, and the outsiders learn no information. Users cannot simply click OK in our solution. We force them to make a choice between some decoy hashes and some actual hashes. The users can operate this remotely over the telephone. Instead of using a T flag, we have 24 bits of the PGP word list, which can be described, it's just 3 words, over the telephone. We don't need a leader election. All members have equal stake. And an integrated secure messaging system we've added to help people understand the relationship between this exchange process, and then once I've exchanged it, how can I use those public keys? And so we've implemented a little messaging system that people can use on the Android side. We have our iPhone, and the Android and iPhone implementations will allow the exchange and then the text messaging on the Android. One of the ways that we add this security is privacy of information is by using the Diffie-Hellman key agreement process. And I know many people in this room are familiar with it. Now, I won't go into the math. Frankly, you understand it probably better than I do. But you know, in that agreement, I have 2 parties in the 2-party case, and I have both parties can construct a public key, and they can share those public keys, and based on the way they're constructed, they can derive a private key offline without having to share it. So in our case, when we have more than 3 people, and we want to use this private key that we've derived to encrypt data, we have to now construct a larger tree, because each of these key constructions are pairwise, just 2 at a time. So we could create a binary tree, which would be nice and even. Let's say we had 4 members, A, B, C, and D. A and B could combine public keys to derive their private key, and C and D could do the same. Then those 2 parties have to take the public form of their keys and share them. So that's another message we have to add to the system to derive the main public key, or the main private key at the top of our tree that we're going to use to encrypt our data. So we want to avoid as many of those messages as possible. So what we're using at the moment is an asymmetric Diffie-Hellman group key agreement, where the first 2 members of the group construct a key, and then they take the public form and pass it on to the 3rd, and so on. So in SafeSlinger, this you've seen a little background of how to construct this tree for authentication, and now here's a little bit of background on how we construct it to protect the information from being discovered by outside members of the group. We have our match nonce again. We have our error nonce. We have our data. Our data is actually now encrypted by our match nonce. Our match nonce is going to become our private key. So at the end of this, we have to make sure we don't reveal that private key through the exchange mechanism. And one of the ways we're going to do that is we're going to begin using this Diffie-Hellman public key we're going to construct and use later. So that match nonce we're going to hash twice. Error nonce we're going to hash once. The resulting hashes will concatenate and hash, and we'll come up with nonce D. And we'll take those triplet values, and we'll hash them together to come up with our commitment. So the commitment's starting to look familiar. Nothing really new here. But now we're sending a commitment. We gather the commitments from all the other group members. We send this triplet of data. We gather it from all group members. We make sure that it passes the hash validation. And now to send an error, and this is actually these 3 values instead of just the data and the nonce, we take these 3 values, order them in a predetermined way to come up with our hash. And we display that hash to everyone, and they spend a few moments making sure that it's the same on every device. This is the similar error one-time signature, and a similar, at least in terms of position, one-time match signature that we'll send out to the group. And if everyone in the group has that signature, we know that this exchange has now been authentic. But we can't reveal that match nonce. So we need a way to reveal that, and we use that Diffie-Hellman public key that we've exchanged before. We may add a few messages to distribute the nodes of the tree if we have 3 or more users, and we'll use the private Diffie-Hellman key that the group collectively derives to encrypt the match nonce. And then once we've done that, we have everything we need now privately to decrypt the data. So now we're doing grouping on the internet. So it's not quite as easy as I have the phones and I can take photographs of them and create an internal network. I have to find a way to do this on the network, and I could send maybe location data, GPS, Wi-Fi location, out to a server where I'm passing these messages, but there might not be granular enough. It may cause me to have several retries. I want something a little more just concise. So we have the users choose a group number between them, but there could be some issues with group leadership. Which number do we use? If everyone gets a different number to identify themselves with. So we tell them to perform some simple math on that number and enter the lowest one in the group. And in sequence, it looks a little bit like this. We have our commitments that we share between these two parties. Once we've sent our commitments to the server and they begin to be stored there, the server passes back a unique identifier to each party. Now that I have that, I can see that on my screen, and I can compare out of band something simple about those numbers, which is the lowest in the group. And I can enter that number and use that to match the rest of the members of the group. And now I can find out who the other people in my group, in this case identified by 3, and I can pass the commitments back. And now, as we've seen before, we can share this triplet of data between these two parties. And we'll validate them, and we'll use them and order them in such a predetermined way to create our hash. We'll display the hash. They will decide, did everything match? And I'll submit my, in this case, one-time match signature for each party. Once I've affirmed that on each party, then they can take those public keys distributed before and derive a Diffie-Hellman private key. And the last thing I'm going to do is distribute this encrypted match nonce, which is acting as our private key, which we previously used to encrypt our data. And now that I have all the pieces, I can decrypt. So this is a good example of the sequence when there are 2 users. When there are 3 users, we have to distribute those nodes, and this is the place we'll do that. I'm not going to walk too much through this. You guys have seen some examples of this. This is a more technical description of each message as it goes across, the data selection, counting, the commitment of the group Diffie-Hellman key and the setup, the unique ID distribution and the user grouping, collection and distribution of that initial decommitment. This word list we're going to create as our hash on the screens that's attesting to all of the data that we've shared for authentication, a comparison, and confirming the integrity of that commitment. Now we may, in the case of 2 users, establish that Diffie-Hellman group key independently, or in the case of 3 users, we may have to distribute the public values of each node as we build the tree. That will occur there at 16. Once we've done that, we can distribute the encrypted nonce, and then we can decrypt our data. So now a little color, a little more color. These are some screenshots from our Android version of the application. When you start up the application, it's going to ask you to select your contact data from your address book. Can I see a show of hands? Do people have in their own cell phone address books contact data that represents themselves, their email, phone number? Does everyone have something like that? I do. Yeah. Does anyone use their real name? Do they have me? You refer yourself in. So a lot of our cell phones will even do this for us. They'll set us up as we'll refer to ourselves as the first person. I have me as the name. So when you start this up, it's going to do its best to find your contact for you, display that on the screen. Although when it says your name, it may be me. And so we try to prevent people from sharing their own name as me in the application. It may, if you try to have that be your contact when you start up, it may ask you to change your name to something that is actually from the third person. But we generate a long-term private key used in the application. And we ask you to choose a passphrase to protect it. The exchange on the first screen looks a little bit like this. I can select my information that I want to share with everyone. I'm pulling this from my own contact in the database, my phone number, my email address. There are a couple of items on here, I think you can see, that are denoted by these little lock icons. And these two values, SafeSlinger push and SafeSlinger public key, are values that we've told from the messaging side of our application to the Exchange API that we want to make sure that this information goes across. We don't want to let the users have the opportunity to deselect. They can deselect their photo or not send their phone number, and that's fine. But the key is critical because that is what is going to make our messages fly in the end. So we click on Begin Exchange. We ask to confirm the number of users, as we discussed. And then we construct that tree. We send it out to the server. Server sends us back a group ID. And we see here it's 5. Other people may have 2. They may have 15. We're asked to find out whatever the lowest number is between everyone in our group. Enter here, and then continue. So now that we've grouped ourselves, we know which of the various people hitting the server are actually the same people that are either in real time on the phone with us or in the room with us. We exchange our decommitments. We construct our visual hash. We represent it here. Whoops. On this verification screen as 24 bits of the PGP word list, which is this list of 512 words split into 2 columns, one of 2-syllable words, one of 3-syllable words. And the way you represent hex data or binary data are each 8 bits of that data get a word, and you alternate the even and odd lists, which are between the 2- and 3-syllable words. And so we have our list here, but we don't know, instead of having just one hash on the screen, we try to prevent people from just clicking OK. We want to make sure that they compare their list with the list on the other phones, or they talk about it on the phone, because we want to prevent them from just clicking OK, and that's one of the ways we get away with that. It's distributed randomly on everyone's phone, and it's not always option 1. So people are forced to make a choice, forced to compare, and either they can indicate that there was no match. They can also just pick the one that is the match for them and continue on. And here at the end of the protocol, I get a list of who I've just exchanged information with, and just told that, you know, to continue on, I'm going to import that into my database, to my address book. So now we can have a little bit of fun. And now that we've done that, we've shared these keys. We've done it privately. Now I have these keys in my list of people I can send messages to, and it has the push token. We use the push as an addressing mechanism to deliver the messages to the other person's phone. So I can select, I can type some secret message, and I can send it. And depending on if I choose an attachment, we give some progress if that might take some time to do. A couple of screenshots of White Rabbit, who's constantly complaining about his schedule. And you know, we have here actually a little attachment which we can download at our leisure. We try to integrate with the Android sharing system. So here in the gallery application, we have our application as one of the ones that will accept some picture that you want to send. So we can do that. We can select the SafeSlinger icon. It'll get imported into our message, and we can send it. Something similar, Bump Technologies. We have somewhat different goals, somewhat similar, but in their case, they're trying to exchange identity information, and they do it by bumping phones together. That accelerometer data and other location-based, say GPS data, are combined and sent to their server, and they're grouped on their server. And so we have to submit that data, and you may have to retry depending on how many people are doing it at the same time. But you know, if we talk about some of the differences, some of the advantages of each SafeSlinger, I don't need that location information or accelerometer data. And because of that, I might be able to implement my system on more phones because I don't need those sensors. As you've seen, the high security properties we've added, the phone works for more than the exchange works for more than 2 users. So I can create this exchange among several people, not just 2. I remotely can do this on the phone. If I have a conference call and I want to do a project kickoff meeting and I want to establish some SVN repository, I can share some secret data by doing this exchange over the phone for up to about 10 users. And Bump is fun because you bump. So I'll just talk briefly about a small variation that we had tried. At one point, we had called our application KeySlinger, but since we're sharing more than keys and messages, it didn't seem to quite fit anymore. But there's this, when we get over 8 users in a group, and to see if we can scale up to maybe many users, maybe 20 or 50, it's very difficult to maybe compare those hashes on each screen, to have all these people in this room talking to each other to make sure that everything is copacetic on each phone. So what we can do is we can give a unique position in order to each phone. And we can give some relative position data to people and ask them to stand in a ring, so that when I'm comparing hashes, I really only need to compare it to the people nearby me. And so once I attest that to everyone in the group, that might be a way of doing this. And if there are so many people in the group, we may want to have our system count for us. And so we can compare what our system described as what we think the count of the people who are exchanging is, make sure that everyone has the same number of people, make sure that everyone has the same word list. One of the reasons that now in the applications we've currently put out, one of the reasons we don't have this feature turned on is because, as you can see here, we're distributing these in the case of 3 or more Diffie-Hellman key nodes. It's starting to add more messages. It's starting to add up. And so as you get up towards 10 users, it begins to drag out a little. And so we want to make this quick and easy for people. So we'll have to do some more performance testing to see if that's something we still want to do. This is a quick little diagram of the exchange portion of the API and the third-party portion of our application, which is our messaging application. A lot of this is in a paper, which I'll give you a link for later, so you won't have to memorize it. When we do address book, when we add this information to our address book, I'm not going to stand on that side of the podium because I'm going to get feedback. Our address book is used by other applications. And if we create an app database within our app that contains the keys we've exchanged, that we can keep that private. The synchronization services, maybe iCloud on iPhone or Gmail, has the power we've given it the power to manage our database in our address book for us. So while we don't know in the future what decisions those services will make about the keys we've stored, but we want to make sure we keep our list of things we've exchanged. That's how we know we've exchanged them. So we create a database in the application, and that's one of the ways I recommend doing this, so that we can validate what we're putting in our address book is the same thing that we exchanged. There's a few notes here about some of the ways you might think address books might manage keys. There's a vCard type, which is a standard ASCII form of importing and exporting contact data. And there's a field there that allows you to store a public key. But I haven't seen an operating system yet that uses it. So some of these things are things we've run into, things we think should work, but don't actually exist because most users aren't using them. So they haven't been implemented. So some future work that we're in the middle of, and we're excited about the iPhone version of the messaging portion. We've got the exchange available for people, but we want to get it to the point where we're doing cross-platform messaging between Android and iPhone. So that's one of the things we're pushing for right now. We want to introduce this feature called secure introduction. So I have this system of exchanging cryptographic keys securely between groups of people. And I have a method of sending messages using those long-term keys. I should be able to, if A and B create an exchange and B and C create a separate exchange, I should be able to forward the public keys that I've exchanged from B's perspective between A and B and sort of extend the web of trust there. So we're looking ahead, and that's one of the things we're going to try to implement. Some advanced features. Some users have asked for being able to import and export their existing public keys. At the moment, the messaging application creates its own private key, and just for ease of use, since most users don't use that public key infrastructure. We really want to get to the point where we can do some open source collaboration and really work with some of these systems that, like Android Privacy Guard is one that I can think of, which is a GPG implementation for Android. And it interfaces nicely with K9 Mail, which is a flavor of the Android Gmail, or not Gmail, but Android Mail application. So getting our authentication, secure key exchange implemented with them, that would be very nice. And of course, more platforms as they become more popular, we'd like to implement. So, so I'll leave you in the end with this, that what we've created is this internet-based communication, which is fast and reliable. We've been able to maintain user privacy. Only other group members learn the exchange information, and the server doesn't learn information or location. We've created user features to make this resistant to user error, so there's no OK to click through. And hopefully it's a simple protocol with minimal user actions to perform. And I'll leave you with that. And there's the link there. We have some installation links for iPhone and Android on our webpage there, and links to the paper and some other resources, some other background information, a few instruction pages, things like that. Does anyone have any questions?
Wouldn't the server know who members of all the groups are? And that would be logged over time, or be able to be collected on the server over time?
Right. So we submit these messages about forming this group and doing these things, but what do we do with this stuff, right? Once it gets on the server, at the moment we have a cron job which removes data over 10 minutes, more than 10 minutes old. We might introduce something that at the very end of the protocol can remove that information a little quicker. But the information that we're sending isn't useful unless you're one of the people in the group. So does that answer your question?
Though it would collect information on who members of groups are. That might be useful information for somebody.
Well, I'm not sure that I understand you completely. What we send to the server, you're saying, so it gets to a server, and even though we may remove it, and the users may send some signal to say, we're done with the protocol, everything's fine, we don't need you anymore, server, thanks, just take it away. It was still sent to a server somewhere, right? So is that information useful to anyone?
I was a member of this group of 6. I was a member of this other group of 8. I was a member of...
Since the information we're sending is all contains these nonces, this randomness, it's hard to associate a user coming in, being part of a group once, with the same user becoming part of a group again at another time. There's no real association. Unless IP address would be the one way to do it, but the contents of the information contain randomness and contain enough entropy that you wouldn't be able to associate it over time.
I have a question about using NFC to bootstrap the Bluetooth connection and also to exchange the nonce data.
Exchange the nonce data.
The end-to-end messages are pretty standardized for changing times, say, especially on Android, and it looks like it's going to move to iPhone, so you guys consider doing that?
We've thought about it. I think once we built this system, there was we weren't sure when this was going to happen. We had a few Android devices that had NFC. Weren't really sure. I think one of the things that we're interested in it, but there's always the issue of, I think didn't someone do a experiment where they were able to take maintain a Bluetooth connection like over a mile, given like a high power Bluetooth signal. So that's one consideration. Another consideration are what's the range of NFC? So if I'm within a few meters, is it practical to have maybe 5 people in that close proximity? Are there some social stigmas about being, you know, I'm in your bubble, right? I'm too close, that kind of thing. Those might be some considerations. And I know this project hasn't used NFC, but I think we have it in the background. I don't know that we've really looked into it.
As an alternative, it's certainly more secure.
Yeah. Definitely. Okay. Thanks, everyone.